Get started. Okay, so we left off, let's see, let me max out the thickness here. Alright, so I think I left off with kind of this made-up data set where we have x and y. We've got 1, 2, 3, and 4, and I said y was 2, 6, 4, and 8, okay? And we drew this. We created a scatter plot, and we said 1, 2, 3, 4. And we said over here we've got 2. All right, and then 1, 2, 2, 6 goes there. 3, 4 goes right there, and 4, 8 is up here, okay? So let me see if I can actually copy this plot. Okay, and then we said, you know, maybe we have a candidate line that goes like this. Sorry, I don't know why I had sound effects there. So we have y hat is equal to 2x. So this is, you know, one proposed line, and we're going to say, you know, okay, if I plug in, you know, x equal to 4, according to the line, I would predict that y hat would be 8, okay? And if I plug in x equal to 1, I would predict that y hat is 2. If I plug in x equal to 2, I'm going to predict that y hat is 4. And if I plug in x equal to 3, I'm going to predict that y hat is 6. Okay? So these are our predictions. So these are the actual values over here. And then over here, we have our predicted values. Okay? And so we can measure this concept of error or residual as kind of the difference between what we predicted for a particular value of x and the actual value. Okay, so we have this concept of a residual, which is equal to the difference between the actual value and what we predict based on the line. Okay, so we might define this concept of error as actual minus predicted, or E as the difference between y minus y hat. Now the book doesn't really get into this, but I think it's an important important part of linear regression, and that's why I cover it in class here. Okay, and so our errors here. Okay, so if I have E is the difference between y and y hat, and this is kind of the symbol we use for residual anyway, is it's going to be 0 because for this first data point, our prediction is right on our prediction line. We have a difference of 0. For this second data point, our prediction is down at 4, but the actual value was 6, so we have an error of 2. Over here we have an error of negative 2, and over here we have an error of 0. Okay, so we can kind of see, you know, here's the difference there. Okay, so far so good with everybody? Yeah? Okay, well good. So let's see. Let me just kind of save this. What, lecture 4, week 3, Wednesday. Everybody else doing, all of your other classes going okay? Yes? No? Maybe? Papers and stuff? Reading? When I was an undergrad, I avoided classes that involved reading. Everybody has their own preferences, right? So some of you probably have tried to avoid every math class as possible, and I took as many statistics classes as I could and avoided as many writing classes. So here I am. Okay, and so here we do this, and then so now what we're going to look, so the way we're going to measure how well or how poorly our line fits is we're going to look at the total squared error. I keep wanting to have double R's in squared. Okay, squared error. Okay, which is exactly what it sounds like. Okay, so we have our error terms, and I'm going to just square them. Okay, so my total squared error is going to be 0 squared, and because everything when you square it becomes positive, I can just ignore the signs. So I'm going to have 0 squared plus 2 squared plus 2 squared plus 0 squared, right? So this gives me basically 4 plus 4, and I get a total squared error of 8. Okay, so the total squared error in this picture, so I can draw little squares. Okay, and so what this basically says is that, you know, if I shade these in, the total area of these squares is 8. Okay, all right, and I just want to make sure that this concept of total squared error is okay with everybody. Okay, because I'm just taking the error column and I'm just squaring it. I mean, if I wanted to, I could have e squared is 0, 4, 4, and 0, right? But okay, so far so good? All right, can I flip to the next slide? Sure. So we'll try this. Okay, and then so that's one line, right? Y hat is equal to 2x is one possibility. And then another possibility, I'm going to draw a kind of another line. It looks, I don't know, something like this. Okay, maybe this isn't so great. And the equation of this line is y hat is equal to 1 plus 1.6 x. Okay, 1 plus 1.6 x. Okay, so we're going to say, okay, well, let's plug in x and stuff and figure out what our y hat would be. Okay, so if I plug in 1, I would get 1 plus 1.6, and I would get a value of 2.6. And if I plug in 2 for x, I would get 2 times 1.6 is 3.2, plus 1 I would get 4.2. And if I plug in a 1.6 again, I would get a 5.8. And I plug in another 1.6 and I get 7.4. Okay, so that's, you know, right here, it's 2.6 and 4.2 and 5.8 and 7.4. Is that okay? And so now we can look at the amount of error that we have. So this would be kind of how far is our data points from the line. And you know, my graph isn't as good. Okay, and so here I have a difference of 0.6, negative 1.6, or I'm sorry, negative 0.6, 1.8, 1.8, and 0.6. Okay, if I do, you know, if I say E is equal to Y minus Y hat, the difference between the actual value and our prediction for it. Okay. And again, I just want to make sure everyone's okay with all of these numbers that I'm throwing up on the screen. Okay. Okay, and then we can look at the squared error. So we can say, okay, well, what's 0.6 squared? Okay, well, 0.6 squared is 0.36. And what's 1.8 squared? 1.8 squared is 3.24. And then, so I will have 3.24 here as well, and 0.6 squared is 0.36. Okay, so my total squared area here, squared error, would be 0.36 plus 3.24 plus 3.24 plus 0.36. Okay, so I can add all of these together. And I get 7.2. My total squared area is 7.2. Alright, so what this basically says is that if I drew little squares for each of these things, and I found the area of these squares and I added them all up, the total area of these squares is equal to 7.2. Okay, and so when we do linear regression, linear regression is also called least squares regression. Okay, so linear regression is sometimes called least squares regression. And the idea is we're going to pick the line that has the smallest total squared error, okay? Because we're trying to find the one with the least amount of squares, okay? So we pick the line with the lowest total squared error. Okay, and so between the two candidate lines that I had, y hat equal to 2x and y hat equal to 1.6x, what just happened here? Cancel. No, something. Okay, so I have this. So this is one possible line, the green line versus the red line. Because the red line has a smaller total squared error, this one, the green line has a total squared error of 8. This one has a total squared error of 7.2. We will say this red line is the better fit. Okay, so the total squared error of the red line is lower than, I'm going to just write TSE of the green line. So the red line is the better fit. Okay, and in the next lab, I don't know if you guys will start that this week or the following week. You will have a lab on linear regression, and you will explore, I don't know, fitting different little lines to your data, and Fathom will draw these boxes and squares, and you'll get to kind of see how this least squared business works, okay? Everything with the lab's going okay, I hope? All right. Great. So I've asked the readers to have your quizzes graded by the weekend, so I'm hoping your quiz scores will show up, and you probably have a sense of how you did on the quiz, right? But your official grade should appear, and then that's that. The midterm next week, so we have a midterm 1 week from Friday, and that's going to cover chapters 1 through 4. Okay, and I intend to wrap up chapter 4 by Friday of this week. Okay, and so you'll have some time to cover it, and we'll start covering chapter 5 the following week and whatnot. Okay, but Chapter 5 will not be on the midterm, on this first midterm. Okay, so we have this. All right, so basically, you can do calculus, okay? To try to find how to minimize the total squared error. Okay, and so if you were to take, if you were to be a stats major or stats minor, you would take a mathematical statistics class and you would do this calculus. Okay, as far as this intro stats class goes, we just say, okay, somebody else did the calculus, and here are the results. Okay, so the results of this calculus say that results tell us that the best fit line will have the following slope and intercept. Okay, and so our slope, do you guys remember what the letter for slope was? B, okay. The slope B will have the value R sy over sx, okay, where R is the correlation, sy is the standard deviation of the y values, sx is the standard deviation of the x values, okay, and then as far as the intercept goes, we have A is equal to y bar minus b times x bar, okay? And so y bar is the mean of the y values, and x bar mean of the x values. Okay, so you just need to get the best fit line, you just need these 5 values. Okay. Okay, so that would be R okay, and we know how to get the standard deviation and the mean, right? So if you were given a list of x and y values, you could calculate the standard deviation and you can calculate the mean if you were forced to. I probably won't make you do that. But the correlation, as far as this class goes, the correlation will be provided to you. Okay, so you can expect correlation to be provided to you. We're not going to learn the formula for the correlation. And nobody nobody finds correlation by hand these days. Okay, it's like, I don't know. You just don't do it. So, yeah, you'd throw it at the computer. You'd say, you know, computer, find correlation for me, or you punch it into the calculator and do that. And that's that. So, okay. All right. So let's do like a practical problem here, okay, with all of this stuff. Okay, so here, let me find the picture I want. This is the picture. Oh yeah, okay, so I think, great. Oh, too big. Okay, so here, this is data on, so I'm gonna try to draw a pretty picture here. All right, so here is a book on Stats 10. That's a heart. Okay, and we're gonna measure its width in millimeters. Okay, and then you also you flip through the pages of the book, and then we're gonna look at how many pages in the book. Okay, and we plot this. We look at a bunch of books, and we say, okay, well, how many pages does the book have, and how wide is the book? Okay, and we plot this, and then we're gonna just kind of fit this line. And we want to say, okay, well, what is the equation of this line? And actually, it was right here. It says width is equal to 6.22 plus 0.0366 pages. Okay, so I've got width is equal to 6.22 plus 0.0366 times pages. Okay, so we'll try our first clicker question of the day. Let me fire this up. So I want lecture 4. Is this working? Okay. All right, so your first question will be, here your answer choices is correlation. B is the intercept. C is the slope. And D is the residual. And the question is, what does the value 0.0366 represent? Okay, so we're gonna try running that. You can start punching in your responses here. So this is the equation of the red line, okay? So if that's not unclear. Okay, so we'll say 5 more seconds to get your clicks in. So 5, 4, 3, I don't know, 2, 1. Okay, so time's up. Okay, it looks like most of you guys got this. A couple of you got it wrong. But, so the answer is indeed C. 0.0366 represents our slope. Okay, so this is the slope. And this over here would be our intercept of 6.22. Okay, so let's this. Okay, so I have 6.22 plus 0.0366 times pages. Let me just kind of highlight. All right, and so what does the hat over width represent? What does the hat mean? Prediction, right? So width hat, this is predicted width, whereas width would be the actual value of the width. Okay, so for a book with 600 pages, the location on the red line would be our prediction, whereas here's this blue dot right here represents an actual book with maybe 620 pages or something, and has an actual width of, I don't know, 26 millimeters or something. I'm just making that up. Something like that. Okay, so if a book has 400 pages, what do we predict its width to be? Okay, so here x will be 400, and y hat or width hat would be what? Okay, and I'm not going to bother making a clicker question out of this. But what would we do? We would just plug in the value 400 into pages here. Okay, so our answer would be 6.22 plus 0.0366 times 400. 6.22 plus 0.0366 times 400, and I get 20.86. Is that good? Okay. What if I have 500 pages? What would my y hat be? Someone just call out the answer. Or I'll do it myself. Okay, so I just do 6.22 plus 0.0366 times 500, and I get 24.52. Is that good? Okay. And then if I had 600 pages, my y hat would then be what? And I get 28.18, right? Is this okay with everybody? Everybody's good. Okay. Well, tell me, how much did my y hat change when I went from 400 to 500? How much of a difference did this make? What did I end up adding to it? The difference between this and this is 3.66 millimeters, right? And what's the difference between this one and this one? The same, right? So if I wanted to go from 600 to 700 pages, what could I just do? I could just add 3.66, right? And this would be our prediction for 700. Okay. So where is this 3.66 coming from? It's coming from the slope, right? So this gives us kind of a clue into the interpretation of the slope. And I'm going to have to continue this on to the next slide here. Okay, so the interpretation of the slope is how much our prediction for y will change okay, if the value of x goes up by 1. Okay, and so in the context of our books here, okay, what we're basically saying is if I add 1 page, and technically a sheet is 2 pages, okay, but basically we're saying if I add 1 page, I'm predicting the width of the book to increase by 0.0366 millimeters, okay, which kind of makes sense because, you know, a page or a sheet is very thin, and so in the quantity, 0.0366 millimeters is a very thin quantity, okay? So as far as textbooks go, or, you know, books go, the interpretation of our slope, this slope quantity is so small that it, you know, we can't really appreciate it until we talk about, you know, making changes of 100 pages, okay? So if I had 100 pages, which, you know, if I go flip over 100 pages in my textbook, this takes me to, I don't know, right around here, okay? So if I, you know, this would be 100 pages, so maybe 50 sheets of paper or something. What we're saying is that if I increase the book by 100 pages, I predict that the width of the book increases by 3.66 millimeters. And, you know, looking at this, that looks like a reasonable quantity for the width of these 100 pages, okay? And so, so in our case, as far as the books go, if I can flip over to the next page, we would say the interpretation of the slope in context would be we predict the width of a book to increase by 3.66 millimeters if the number of pages goes up by 100. If the pages goes up by 100. Okay, so, you know, kind of the generic interpretation of the slope is if you increase x by 1, this is how much your prediction changes. Okay, and it's important that you have somewhere in there your prediction changes by this much, or we expect y to change by this much. But don't say that y actually does change by this much, because increasing a book by 100 pages does not necessarily mean that it will definitely go up 3.66 millimeters. It's just saying, you know, based on our understanding of the other books, this is what we're predicting, okay? But it's not like a definite type of thing, and that's why we have the something happened. That's why we have the hat over over the thing here. Okay. Okay. What else? What else? So we predict the width of the book to increase by 3.6 if the pages goes up by 100. Okay, so that's the slope. All right, the intercept is 6.22. Okay, and the interpretation of the intercept is our prediction for y if we plugged in 0 for x. Okay. All right, now sometimes it does not make sense to plug in 0 for x. Sometimes okay, and in those cases, your intercept will not have a practical interpretation. Okay, so for example, we could try to predict someone's arm span based on their height, okay? And we can have some kind of equation or formula. And what we might find is that, you know, you get something here, okay? And maybe we can predict arm span based on height very well. But can you have a person with a height of 0? No. Okay, so we cannot plug in 0 for our x variable, which would be height. Okay, and because you cannot plug in 0 for x, the intercept will not have a practical interpretation. Okay. Can we imagine a book with 0 pages? Maybe, maybe not. Can we? I kind of can. Okay, so here, you know, our intercept is 6.22. You could imagine tearing all of the pages out of your book, okay? And what would you be left with? You would be left with the covers, right? And so if you were to measure just the thickness of the covers, perhaps you would get a number. Something just happened. Perhaps you would get a number close to 6.22. So, you know, the intercept in context here would be, you know, we predict a book with 0 pages to have a width of 6.22 millimeters. Okay, so maybe, you know, this could be, you know, maybe the width of covers. All right. Something like that. Okay, is that okay? All right. All right, so I want to talk about the distinction between x, you know, which is x and which is y, okay? So our x variable is the variable we use to make a prediction. So we use we're going to make predictions based on the x variable, okay? Other names for the x variable include the predictor variable, the predictor, the explanatory variable, because it is the variable that explains things, or the independent variable. Now, I don't really care for this term, but the idea is that the variable x is independent to, I don't know, to vary, that we have, you know, maybe some control over the x variable. The y variable, on the other hand, is the variable that is being predicted. Okay, And so this we will say is the predicted variable. Or if you're using explanatory variable, we will say this is the response variable. This is the variable that responds to our change in inputs. Or we will say this is the dependent variable, the variable that depends on kind of the inputs of the equation. Okay, so so I'm gonna kind of post up a couple clicker questions here, and we'll try this out. Do you guys have all this written down? Okay, so let's something happened. All right, so this will be a clicker question. All right, and your answer choices will be total gas consumed in gallons. Okay, so these are your answer choices, and the question is, you want to predict fuel consumption based on the distance of an upcoming road trip. Okay, what is the explanatory variable? Okay, all right, so I'll start the thing, so you can click your responses, and they are registering. You want to predict fuel consumption based on the distance of an upcoming road trip. What is the explanatory variable? Okay, we'll say 10 more seconds to get your clicks in. Okay, 3, 2, 1. All right, let's see. And that is indeed the answer. Answer is answer choice A. We are looking at the total mileage of the trip. Okay, this is the explanatory variable. This would be the, so this would be explanatory. Wait, hang on a second, I got one more. Explanatory and the response. Okay, and then so your next question will be, what is the form of the regression line? Okay, you got A, B, C, and D. Okay, so here we will have Okay, so go ahead and get your clicks in here. I think this one's also rather straightforward, but so yeah, you can get your clicks in here. We'll say 10 more seconds. And 5, 4, 3, 2, 1, and let's take a look. Okay, and that indeed is our answer choice. Answer choice C, we are looking at fuel as a result of mileage here. Okay, we'll end there, and we'll see you guys on